In this video, we're going to discuss the basic types of organometallic reactions. Although we're going to discuss these individually, oftentimes, and especially in catalytic processes, you see these different basic reactions performed sequentially, taking you from your initial reactants to your final products. So for example, the Wacker process is an industrial process for the conversion of ethene plus half an O2 in the presence of palladium tetrachloride and a copper 1 source into the corresponding aldehyde. Starting with palladium tetrachloride, you add in acetylene, displacing a chloroligand through an associative type mechanism on that square planar palladium compound, forming the pi species here. In a series of steps, an OH from water is added to a carbon on that ethylene through a migratory insertion type reaction. You then lose a chloride. You undergo a hydrogen elimination process, reforming the CC double bond and this palladium hydride species. You then undergo a hydride insertion, forming this alcohol ligand here, which then reductively eliminates, forming your aldehyde species and palladium 0. This palladium 0 is oxidized back up to palladium 2, gaining the 4 chlorides, forming palladium tetrachloride from copper 2+, which itself gets reduced down to copper plus. This copper 2+ is regenerated from O2, which oxidizes the copper plus up to the copper 2+, forming water from half an equivalent of O2. What we're going to do now is discuss basic organometallic reactions one by one, and I'm going to give some examples of each of these reaction classes. Although most commonly seen in transition metal organometallic chemistry, you also see these reactions in other transition metal chemistries and organometallic chemistries not involving transition metals as well. We're going to start by examining a migratory insertion reaction. With a migratory insertion reaction, you're inserting one ligand attached to the metal center to another ligand in this type of manner. And oftentimes, an exogenous ligand will coordinate to that vacant site. The types of acceptor ligands on the migratory insertions are typically COs, carbon-carbon double bonds, carbon-carbon triple bonds, benzene ligands, CP ligands, and similar ligands. The X groups are typically hydrides, alkyls, arenes, and carbonyls, while L is generally any type of Lewis base, be it a phosphine ligand or even solvent. Some common features of migratory insertion reactions. There's no net change in the formal oxidation state of the metal. So the metal stays in the same oxidation state. In order to occur, X and Y must be ligated in a cis-type fashion, or else you won't get the migratory insertion process to happen. And finally, If your complex is chiral, then the stereochemistry will be retained. Migratory insertions are typically broken down into two different types, a 1-1 and a 1-2 insertion. A 1-1 insertion involves the insertion of the ligand X into the first atom in a ligand attached to that metal center. An example of this is the chemistry that methylmanganese pentacarbonyl undergoes. Here you get a migratory insertion of the methyl group into the carbon on the CO ligand. Upon formation of that 5-coordinate species, an exogenous ligand such as CO can coordinate in. And you form this species. So this is a 1-1 insertion. In addition to a 1-1 insertion, you can also get a 1-2 insertion, where now if you have a ligand that's coordinated in an A-to-2 type fashion, you can get insertion into the ligand, the atom on the ligand, that's not directly coordinated to the metal position, and instead is in the number 2 position. So 1-2. This is a 1-2 hydride insertion. An example of a 1-2 migratory insertion is a special type of migratory insertion called a hydride insertion, or a 1-2 hydride insertion, where here we're going to be inserting a hydride ligand into a carbon-carbon double bond. And what we're going to look at is an iron CP star. So CP star is just like CP, but each carbon on the cyclopentadienyl ring has a methyl attached to it. This is bound in an A-to-5 fashion to iron. We're going to have this particular set of ligands bound in the other 3 vacant sites. This will undergo a 1-2 insertion, where I'm now going to abbreviate that ligand as CP star. Where we now have that hydride inserted into the carbon on that ethylene ligand. And this is bound into the metal center through a so-called agostic interaction, where the electrons in that CH bond are weakly coordinating into that iron compound, or iron center. Upon the addition of another phosphine ligand, you form your final product, where the hydride ends up on that methyl carbon. A large class of reactions fall under oxidative addition reactions. In these types of reactions, a metal center in some N+ oxidation state will add an AB type ligand Upon addition of the ligand, the metal center is oxidized by 2 electrons, and you form an A and a B bond. So formally what's occurring is you're breaking the AB bond, you're forming a metal B and a metal A bond. One of those electrons comes from the AB bond, the other one comes from the metal, and the same for the metal B, where one comes from the AB bond and the other comes from the metal site. Hence the oxidation by 2 electrons of that metal center. So you're oxidatively adding a ligand across the metal. The general requirements for an oxidative addition reaction are that you have to have a metal center in at least the D2 d electron count in order to be oxidized. Furthermore, the metal center must be coordinatively unsaturated with 4 coordinate complexes most commonly undergoing oxidative addition type reactions, especially from late first row transition metals. An example of an oxidative addition reaction would be the addition of methyl iodide to this platinum 2 species. So you add methyl iodide to this platinum 2 species, and you form the 6 coordinate octahedral compound, where we've gone from a formal platinum 2 D8 complex to a platinum 4 D6 complex, going from 4 coordinate square planar to 6 coordinate octahedral. The reverse of an oxidative addition is a reductive elimination. So here, what you're doing is you're taking a species that has a relatively high coordination number in an oxidized metal site, you're reducing it by 2 electrons and forming that XY bond and releasing that from the metal center. So, some observations about reductive eliminations. So that these are go through concerted mechanisms. X and Y must be cis to one another. High metal charge enhances the reductive elimination reaction, and if you have an electron-rich metal center, it will slow down the reductive elimination reaction. As an example, we can look at the reductive elimination from a square planar palladium species. So this square planar palladium 2 If you dissolve this up in a solvent like DMSO and you heat it up to 80 to 100 degrees C, what you form is the two coordinate palladium phosphine species, plus you couple together the two methyls, forming ethane. So you've reductively eliminated from that palladium center. You've gone from a palladium 2, D8, to a palladium 0, D10 species. You've reductively eliminated two methyls, forming ethane. The last series of reactions we're going to talk about are hydrogen elimination reactions. And what we're looking at here are the elimination of a CH bond on the ligand, forming a metal hydride. These are broken down into alpha, beta, and gamma hydrogen eliminations. I'm going to do these out of order, starting with the most commonly observed and going to the least commonly observed. The most common are the so-called beta hydrogen eliminations. In these reactions, you're removing a beta hydrogen and you're creating a metal hydride. So you form this. And the beta hydrogen eliminations are the most commonly seen hydrogen elimination reactions. As an example, we're going to look at another platinum 2 species. So a square planar bis ethyl species. This compound can lose a phosphine ligand, becoming 3-coordinate. And this is now set up for a beta hydrogen elimination, where it can lose one of those beta hydrogens, forming the platinum hydride species. This is now set up for a reductive elimination here, releasing ethane, and then ligation of your lost phosphine will eventually generate the resulting platinum 0 compound. So in this example, we have ligand dissociation followed by beta hydrogen elimination, followed by reductive elimination of ethane, followed by the association of the phosphine, forming the 3-coordinate platinum 0 complex. Less commonly observed than beta hydrogen eliminations are alpha hydrogen eliminations. Although originally thought to be rare, alpha hydrogen eliminations might be more common than originally thought. It's just that the product from an alpha hydrogen elimination might be so reactive that other downstream reactivities occur, and it might not be obvious how the end product would result from the original alpha hydrogen elimination species. As its name suggests, in an alpha hydrogen elimination, you're removing the hydrogen from the alpha carbon of an organic ligand, forming the resulting metal hydride and a carbene ligand. An example is this molybdenum CP methyl species, which can lose a phosphine ligand forming this 3-coordinate compound, which is highly reactive and undergoes a beta hydrogen elimination. The resulting carbene ligand is highly reactive and can capture that free phosphine, forming this as your end product. The last reaction we're going to talk about is the so-called gamma hydrogen elimination. Here, a hydrogen from 3 carbons out is being lost from the ligand and donated as a hydride into the metal center. So, you form a species like this, where you have this 4-membered metallocycle. These types of reactions are rare. You typically need ligands that have tert-butyl groups attached to them to block reactivity at the alpha and the beta hydrogens. And you typically need to form a very strong metal-carbon bond, which is only satisfied with transition metals such as platinum. As an example, which undergoes a gamma hydrogen elimination from one of the methyl groups on the tert-butyl rings. This forms this complex here, which then undergoes a reductive elimination of this hydride and this organic ligand here. So it's going to release that compound and make that resulting organometallic species.